inviting me to speak over here. Okay, yeah, so thanks, Jyoti. I think you're the sole organizer, so thanks, the organizer. So yeah, so this is, I'm going to speak about two separate work that I did, one with Vern Paulson, one with Jeremy Levick, but the later work is kind of very on a similar theme, so I just wanted to sort of mix them together, although I'm talking very less about the later talk. Mainly it'll be the work with Vern Paulson. So it's since it's a math seminar, I don't want to go too much into discussion on physics, partly because I myself not very clear about the actual physics that's happening behind these, but the motivations certainly lie in quantum mechanics and quantum information theory. But this talk does not require any prior knowledge of quantum theory. So it's mainly solely based on linear algebra and a bit of functional analysis. So let me start with the outline of this talk. So I would first like to speak about this finite input-output games, and that's where I say that is, the motivation is here. So I'd like to sort of talk a little bit about this without going too much into it. Then some examples of these games. So these are basically some sort of a games played by two people against a referee. I'll give you some examples. And then one specific class of these games called synchronous games. And related to that kind of game, there's some probability distribution called synchronous densities or synchronous correlations. Turns out that kind of probability distribution has a tight connection with some C-star algebra theory, traces on C-star algebra theory. So I'm gonna say the main result on that topic. And then the follow-up to that is another new class of games called bisynchronous game. And related to that kind of game, there is corresponding correlations called bisynchronous correlation. And what would be the right analog in terms of the C-star algebraic connection from synchronous to bisynchronous is this the quantum permutation group, or the traces of quantum permutation group.
Mizanur, sorry to interrupt. So
yeah.
I don't know if others are facing, I'm just facing a lag in video and your voice. So maybe if you could just switch off the video, or maybe that will.
Okay, yeah, sure.
Yeah.
It's always better. Okay, okay. Let me know if it is helping.
Yeah, sure.
Okay, and all right, okay. So and then after having all these, there's this connection to completely positive maps to these kind of games that that I will talk about, and this is a very special class of completely positive maps. These are called factorizable maps, and these are studied by Haagerup and Haagerup Musat in some different context. And after that, this concept of positively factorizable maps would come into play. But I'll just give the definition of this kind of maps and leave the rest to like unsaid, because it's slightly, it will be more involved, but these points would fill up a lot of time. And hopefully, if the time permits, maybe we can discuss a couple of problems. So that's the plan. So let me start with this. What is this input-output games, or sometimes it's called local games. It is basically what's happening is so there are two players playing this game against a referee. So Alice and Bob both are in separate places. They're cooperating and non-communicating. Cooperating means they're playing playing with each other against the referee. And non-communicating means once the game starts, they cannot communicate with each other. The idea here is the referee would ask each individual a question, and they have to output with answers, and the referee would check that, upon receiving the questions, both Alice and Bob, whether they produce the right answer. So like everything, each game, this kind of game would have a rule function, and the rule is, is basically a map from this IA cross IB cross OA cross OB to 0, 1, that lambda x, y, AB means that if Alice and Bob receive inputs x and y respectively, produce outputs A and B. And if the value of lambda is 1, then they win, and if it's 0, then lose. So the referee hands in two questions, x and y, to Alice and Bob, and they answer with A and B. But note that because they're non-communicating, Alice doesn't know what question Bob was asked. Bob doesn't know what question Alice was asked. And similarly, they don't know what the other player outputs are. So that's what I mean by non-communicating. So they know the game, they know what they need to answer from, but because the lambda depends on four choices, it has to match. The right thing has to match, and that's when they win that round. And each round like goes on one after another. But what is interesting is so they can come up with a strategy beforehand, before playing the game. And the idea is to optimize their chance of winning, right? And so they just don't hand in the answers randomly. There's some sort of a measurement or some sort of an experiment they do upon receiving questions, and based on the output of that experiments, they provide answers, and that's how they have a chance to optimize their winning. So if you say PABXY is the probability of output AB upon receiving XY correspond to Alice and Bob, then you call a strategy to be perfect if the probability with which they output AB upon XY is always 0 when the lambda function is 0. So lambda XY AB 0 implies the probability AB given XY is 0. That's what you call a perfect strategy. Now, broadly, there are two ways to come up with a strategy. So we will mainly highlight on what kind of strategy and mathematical structure about this strategy. So it's a 4-tuple in our n square k square, where n is the input size, k is the output size, and we'll mainly see that how can these probability densities arise from different. So it turns out that there are broadly two math models that you can describe your strategies coming from. So let's see. So first of all, there's this one strategy called the classical strategy, or the probability that come out of this kind of strategy we call classical correlation, and that's basically it is it's like a measure theoretic description. So you have a shared measure space, omega mu, and for each input x and y, Alice and Bob have functions from that omega to the output set, fx and gy, and the probability is just the measure of the points that gives you the right answer or the appropriate answer. So with this probability, they would answer AB given x and y. So that's the classical correlation. It turns out that classical correlation is a convex, closed convex set, and the extreme points are basically like 1-0 function, like the step function. So given input x, f of x a would be 1 if they produce the answer a, 0 otherwise. So and those extreme points would be, if you take the convex combinations of these extreme points, you get the classical or local correlation. So it, in some sense, it is like a predetermined. So you already have, before the game started, Alice and Bob have determined what answer they would give. Have they received, let's say, some x and some y. So they have predetermined the output. That if I get x, Alice and Bob determines that if I get, let's say, some x, I'll get that a. And Bob says, if I get this y, I will answer with that b. So there is no measurement. There is no other thing going on. It's very like a, as you do in a classical world, or as you do in any normal game. Yeah.
What is omega? I mean, can someone specify that?
It's just an arbitrary, it could be a finite set. It's just a measure space that you can describe, where your mu, your fx are taking values on. So in some cases it could be just a just a function from a discrete set, and fx is basically taking any point to the output number a, something like that.
Yeah, okay, thanks.
And the other scenario, the other class or other scenario with which this probability could come is this called quantum correlation. And the description of this is as follows. So what happens here is, like, you can imagine that Alice and Bob are in separate places, and they both have access to some labs and some measurements. And upon receiving each input, they perform an experiment, and they will produce an outcome. But they just don't do it individually. They do individually, but their labs are connected in a, their labs are connected in what we call this entangled. So they're like, there's some information that very subtly that they can transmit from each other. Although they're not physically communicating, but because their labs are shared by an entangled state, it is possible that measurement of one party can affect the measurement of another. So if Alice measures some experiment, and based on produce an output that can affect, and Bob can perform based on that, Bob can perform an experiment that will output another B, and their answer sort of it will be in sort of it will not be as random as the before. It will be more coherent, so that their winning chances are better than the classical one. But in any case, the way it arises mathematically has this description. So imagine that they have two Hilbert spaces, and they have a bunch of projections. And if for each input, if you, it's like a POVM. So you sum on the output set, you get the identity on the Hilbert space, both sides. And you have this entangled state. That means you have a, let's say, a pure state in the tensor product, which is not of the form, which is not like a product vector or product. Yeah, it's not a product vector, right? So anything which is some linear combination of product vectors is called entangled vector in the tensor product. And I don't know what happened. And their probability, as I said in the previous slide, probability is basically the measure in the classical case. In this case, the probability is obtained by looking at these POVMs tensoring with the other POVMs. And just so this is now an operator acting on Hilbert space HA tensor HP. So let that operator act on this entangled state psi and take the inner product with itself. So you get a number between 0 and 1, And that's how your quantum correlations arise. Now, it has been proved that certain games, if you play with just the classical way, there is you have a certain chance to winning a game, irrespective of the size of the game, irrespective of any other constraint. There's a definite chance of winning a game. But if you play that game with entanglement as a resource, the chance of winning this game is bigger than what is possible classically. So there are games where this phenomena, having an entanglement resource has proved to be an advantage. But the way it manifests in mathematical modeling is this: your probability is basically just this number arising from this P of VMs of each respective parties. So let me give you a quick example of this. So recall that a graph homomorphism is basically you have two graphs, and then a homomorphism is a function from the vertex set of G to vertex set of H. That has this property that if every time G1 and G2 are connected with an edge in G, the function should respect this connectivity relation. So that means TG1 and TG2 should also be connected in H. So you can turn this concept into a non-local game. So here the idea is, sorry, I don't know. So here the idea is the referee. So there's two graphs G and H. The referee hands in Alice and Bob two vertices G1 and G2, and they have to reply with vertices from H. And the condition is they have to show that every time G1 and G2 are connected in G, their output should have the property that they're also connected, given G1 and G2 connected. So that's so more or less it's like a graph homomorphism. So the referee is asking for a homomorphism, but note that the referee is not asking for a function. All the referee is asking, here's two vertices, just give me the other two vertices in H. Here are two vertices of G, give me the other two vertices of H, where this relation would be valid. Now, presumably you can think that if there was a homomorphism, graph homomorphism between G and H, you can always use this function and produce your answer, right? And that would be and in each round you will win the game. And it is true that if the two graphs had a proper homomorphism, then you use that function and you produce the output. And you can convince the referee that there is a homomorphism, and this is the homomorphism. Well, you can convince the referee that there is a homomorphism. But what is interesting is with entanglement as a resource, it has been proved that there are graphs where there is no actual homomorphism. But in each round of this game, you convince the referee that there is one, just because you are very concerned with not the whole mapping, you're concerned with this local property of this game, which is the connectivity property. So if you play this game with an entanglement as a resource, there are graphs where the graphs don't have actual homomorphism, but you can win this game with probability 1 in each round. And that's one of the remarkable things that came up with this work from Menziska and Robertson, 2012. But there is a slight one more condition to this game, is that if referee sneakily asks this, give away the same vertex, right? To, let's say that he gives G1 and G2 both Alice and Bob the same vertex, they cannot produce different vertex because that's not even a mapping, that's not even homomorphism. So they also have to come up with a same vertex of H. So that's another rule that they have to follow. Anyhow, the theorem says that A and B, the Alice and Bob, win with classical strategy if and only if there is an actual homomorphism. And there are graphs where there is no classical homomorphism, yet they win this every round of this game with quantum strategy using entanglement as a resource. So there are other examples that you can imbibe from concepts like graph theory or metric space, or there are other things in computer science. There are plenty of games. They call it prover system. You can always convince a referee about something that probably classically not true. And the very non-local, well, it's very, the structure, the way the games, the rules of the games are, it is possible actually, without producing an actual, let's say, map or a homomorphism in this case. So I'll tell you more about examples and other things, but just to get you started with how these games work in this setting. So let's focus on the way that we obtain our probability or the.
Actually, for matrix space, if you replace and you demand this kind of thing, then you need, if G1, G2 has the distance, let's say some D, then you want this TG1, TG2 has the same distance. So T is
Exactly.
Right?
Exactly. So you basically want an isometry. And there are, I don't think whether it has been written down somewhere, but there are some people working on this thing that there are metric space which are not isometric, but with this kind of strategy in mind, you can convince the referee that there is an isometry. Yeah.
Okay, thanks.
There is a question in the chat.
So, okay, I
yeah.
did not see the chat, sorry.
It's written no loops in the graph. That's the question.
Yeah, sorry. Yes, no loops in the graph. Yeah, it's a loop free. Thanks. Yes, absolutely. It's a very, yeah. There's no loop in the graph. Okay, let me see if I can access my chat. Okay, I hope that there's no other question.
Yeah, that's all. I'll keep you updated. It's all right. Continue.
Okay. Okay, so let's concentrate on these various probability distribution or correlations, just to try to understand what are the basic properties of those sets. So, but if you look closer, the second model that I described to you, I said that the Hilbert spaces are finite dimensional. Now, you can ask yourself that what if I allow an infinite Hilbert space, and what does it even mean, in a finite dimension? Because in finite dimension, you can model your state space from physics terms, but if your number of elements are a number of input sizes, if it's too large, often you treat that as an infinite dimension. So there is no there's no real problem in going to infinite dimension. You can ask, what if I allow my probability correlation coming from infinite dimensional state space? So anyway, so if you start looking at all those models in more detail, what you'll find out that let's just, for the time being, let's just name these sets. C-log is the collection of all those PABXY that come from those measure spaces I described. That's a closed compact convex set. Any round where your strategy are basically drawn from this set is called a classical strategy. Then you have this finite dimensional model, quantum correlation. We call it CQ. And we call game with this strategy a Q strategy. QS is the quantum spatial, which means it is the Hilbert space are no longer finite dimensional. You will allow them to be infinite dimensional. It's called QS strategy. There is no reason to believe that these CQ sets are closed, and in fact they're not right now. We know. So you take the closure in Euclidean topology, and just denote that to be the quantum A, quantum approximation, called QA strategy. And then the very big, as a like a sort of a the mother set sort of set inclusion is this CQC, which is basically a commuting model where you don't take your entangled state to be coming from a Hilbert tensor product model. You just Imagine they both share an entire universal Hilbert space. And the operators, the respective operators they have, they commute with each other. And probability A, B, X, Y given by that inner product. This is the largest model. I will tell you more on these sets when it comes to synchronous games, because there it is easier to describe these sets. But anyhow, these are, let's say, these are possible models that I can describe the probability densities. Now, why these are interesting? Well, it was now it has become a big research topic, but it was actually found out these different models by Cyrilson in '93, and he wondered whether all these quantum models that I just described, QC, QA, QS, and Q, these are all the same, or these are different, or is there any separation between these? And until 2011, this problem or these sets even became more popular because Ozawa and Marius Junge and other collaborators, they related this famous Cohn's embedding problem with these two sets being equal for every input and output set. So CQA, the approximation version, being equal to CQC, the commuting version, for every input n and output k. If these two sets are equal, then it turns out that you'll have a positive answer to the Cohn's embedding problem. So, so people trying to understand these sets more closely and see what can you say about it. And it's what do we know is not much actually. So first of all, first observation is you can always see the quantum being the superset of log. So your classical strategy with this probability distribution, it can always embed into some finite dimensional Hilbert space and say that, okay, your classical strategy is basically is a part of something quantum. So CLOC is also always a proper subset of quantum. By definition, CQ is subset of CQS because in QS you have allowed infinite dimension. And of course, these two sets lie inside the closure of CQ. It just happens that CQ closure and CQS closures are same. It's not trivial, but it has been proved. And all these sets, they lie as a subset of CQC. So CQC is this big space. And like until recently, well, it's not that recent, but still 2017, it turns out that the CQ set is not closed. And to prove that, Slofstra came up with some brilliant group representation theory method to prove that if you take your input as large as 100 input and output as 8, then this set is not closed. And in the same year, Paulson, Daikema, and Jitendra Prakash, they proved that even CQS is not same as CQA, which means that CQS is not closed for input n equal to 5 and k equals 2. So they brought it down, the input and output size really to very small, like 5 and 2. But their method was also very, very nice. They used some sort of a graph correlation function to prove this. And a year after, Stark and Colarangulo proved that CQ is, so the finite dimension and infinite dimension actually matter. So there are games where there is a separation between, if you play with strategies coming from finite dimensional Hilbert space versus you play a game with strategies coming from infinite dimensional Hilbert space, you can do better in infinite dimension. So there is a separation. So the dimension does matter. And the last major thing was this G. Natarajan, Vidit, Wright, and Yuan, who announced in 2020, last year, a result on quantum complexity theory that actually disproves this version of set equality, CQA and CQC, which then negate this Cohn's embedding conjecture. So through this machinery, there is a claim that Cohn's embedding conjecture does not hold, but we don't have an operator algebraic proof yet. So I mean, I resisted myself to write down the statement of Cohn's embedding problem because I didn't want to go into too much of operator algebraic terminology because it would require some 2-1 factors and all. So I just, if you're not from the operator algebra, Cohn's embedding problem is one of the major open problems in operator algebra. And through this work of Marius Junge, Paulsen, and others, there's a connection with that problem with these two sets being equal, CQA and CQS for every input and N and K. And it turns out recently that these groups show that these sets are not equal, and hence Cohn embedding problem is not true. So as I said, that the cleanest way to describe these sets in terms of an operator algebraic expression is synchronous game. So these games are actually quite easier in terms of the rules. So first of all, the Alice's output, input and Bob's input are same, so the same set, and the output sets are also the same. And the condition, you call a game to be synchronous, or you call a perfect density to be synchronous, is if you receive the same input, you cannot produce different output. So if a referee hands out the same question to both Alice and Bob, they have to come up with the same answer. They cannot answer with different answers. So you could think that this can be a very commonsensical condition. Every game should have it, but there are games where this condition doesn't hold, so they're not synchronous. But turns out that this tiny little condition makes a lot of difference in terms of the way the mathematics, like at least this part of the mathematics go. So a game with this property that the players have to send same output given the same question is called synchronous, and you describe this game as this script G, I, O with a lambda. Now, why this game gained popularity is, okay, before going to that, let me give you some example. So the graph coloring game is synchronous. Graph coloring is the same concept. So you want to color a graph means you want to just color all the vertices with different colors, but the idea is no adjacent vertices should have the same color, right? So the referee gives out vertices to Alice and Bob. Alice and Bob output with colors. And the only condition is they cannot, the adjacent vertices cannot have the same color. That kind of game, if you put it in this format, is called the graph coloring game. And that's a synchronous game because you can check that if they give you, if the referee gives the same vertex to both of them, they have to come up with the same answer. Otherwise, they cannot win because that means there's something fishy going on, right? So that game is synchronous. Graph homomorphism game that I described, that's the synchronous game. Similar concept with graph isomorphism, that's also synchronous. And there are many other games which are synchronous. I just wanted to focus on the graph related to graphs because it's easy to describe. And the major theorem in this game is basically is this from Paulsen and his collaborators there in 2014. So what they said that if you take probability distribution from these synchronous class, and you take the maximum one, the QC class, then you can associate a C-star algebra generated by these projections indexed by this input and output set. The projection satisfy this P of VM condition. And you have a trace on the C-star algebra such that your probability is basically given by this moment expression. So tau of EXA, EYB. So having a synchronous QC correlation is equivalent to having a C-star algebra generated by projections with a trace such that your probability is given by this. Now, this immediately opened up a lot of questions and a lot of avenues. So first of all, what if your probability is Q instead of QC? Like finite dimensional algebra space. Can you associate something? Can you say something about the algebra? Yes. So what you can do is you can have a finite dimensional representation of this algebra, which means you can literally take A to be some represented in some matrices. At that time, they didn't have an answer to QA and QS, I guess, QA. So later, I'll talk about it later. So that this theorem kind of opened up this avenue of understanding these synchronous correlations versus C-star algebra with trace arising like this way, and these moments. And what can you say about these various representation of the C-star algebra? And since then, there have been plenty of work in this direction. I don't want to get too much into it. I'll quickly sort of skip those and come into this the highlight of this talk, which is the bisynchronous game. So it's basically a follow-up to synchronous. Here you want a density to be bisynchronous if it has the synchronous condition, which means XX PAB is 0 if A not equals to B. And it also has this property that if your inputs are different, then output also have to be different. So you cannot have same input, same output with different input. So slightly different than synchronous, it's slightly more constrained. So it is a synchronous game with an additional property. And it turns out that the graph isomorphism game is a bisynchronous game, and graph homomorphism game, where one graph is Kn, the complete graph, and the other graph could be any other graph, is also a bisynchronous game. And there's a funny way that you can turn every synchronous game into a bisynchronous one. In anyhow, what's the relation to these games in terms of this operator algebraic expression that we had in synchronous game is what is the content of the next slide. But to say that, I need to say a little bit about quantum permutations. So imagine when you think about a permutation matrix, is basically a n by n matrix with 0 and 1, where each row has 1 and each column has the number 1, the rest is 0. So you can sort of quantize it, or some sort of a non-commutative version of it, is you have an n by n matrix with projections in self-adjoint idempotent, with the property that along each row, the projection will sum up to the identity, and along each column, the projection will sum up to the identity. Wherever these projections belong, identity is in that algebra. It could be matrices, it could be operators, it could be elements in a C-star algebra, or even in a star algebra. So if you stack them, stack some self-adjoint idempotent into an n by n matrix, then it is automatically the case that the matrix that you'll get is unitary, which means U star U and U star will be this identity in the n amplification of the space. And now this is, and the C-star algebra generated by these projections is called this quantum permutation group. And there's plenty of work, the experts, and there are like plenty of work has been gone into quantum permutation group since its introduction, and it falls under this even bigger theory of quantum groups. It's usually denoted by OSM plus. The representation of it on every properties are very detailed, like it's studied quite extensively, but still there are a lot of things that are not known. So I will say that if, okay, all right, so that's all I needed for the result, to state my result. And here is the result for a bisynchronous density. If you start with a bisynchronous with same input and same output, QC, then there is a tracial state on this universal C-star algebra, like the quantum permutation group, which you denote by OSN plus, such that this P is given by this moment. So it is exactly like the synchronous case, but in that synchronous algebra, what you didn't have was this magic unitary or this quantum permutation that I just described. In this game with this input n and output n, you actually have a quantum permutation. And various strategies correspond to various representation of the group, which means if you start with a QA strategy, the quantum approximation, that means that you can represent your quantum permutation group inside an ultra power of the hyperfinite 2-1 factor R omega, such that this PAB is basically given by the trace, the canonical trace on R omega there. QC is just any OSN plus with a trace. And if you start with a Q, just a quantum, then your quantum permutation group would
so this QSN plus this quantum permutation group, so is it cone embeddable always? No.
Is it what embeddable?
The condition you just gave in the last slide.
Yeah.
So if and only if there exists unital star homomorphism pi of this into an alter power of 5. So that means this quantum permutation group has to be cone embeddable, right?
Yes. Yeah. Yeah.
It's not always the case, I think.
Yes, but if it has to come with a bisynchronous one, it has to be embeddable in coming from an omega. Yeah. Yeah. In general, OSN plus doesn't have to be, but I'm saying that if it has to be bisynchronous, then that the algebra that you get, it can be represented as inside the hyperfinite 2-1 factor. Yeah. And if it has a Q strategy, then your OSN plus has to be inside a finite dimensional. So basically, your projections are coming from a finite dimensional C-star algebra. And if you're looking at the local strategies, basically your projections are coming from some abelian C-star algebra, or the space that you generate is basically sit inside an abelian C-star algebra. So these various representations of OSN plus would actually correspond to the various strategies of the bisynchronous games. That was our theorem. The main contribution was from synchronous. We get into bisynchronous by looking at the magic permutation suddenly pops out of these conditions. So that's as far as these games go. I would actually shift the attention a little bit towards these completely positive maps, and I would see that these games actually give rise to some completely positive maps. They come from, the motivation was actually Haagerup and Musat's work on asymptotic Birkhoff conjecture, but I don't want to go too much into it. So imagine you have a linear map from n by n matrices to itself, and you call such a map factorizable if you have a C-star algebra with a trace and a unitary in the bipartite system, such that your map could be written as this. So you take your X, a matrix, tensor it with the identity of the C-star algebra, and pick that unitary and do an unitary rotation, and then trace out the ancilla, which means you take a partial trace of this element U star X tensor 1 U, and the partial trace is basically the tau that on A. So then you get back onto Mn. So if you can write your phi like this, then you call such a map factorizable. Of course, there are certain maps, there are maps which are not factorizable. Turns out that these maps have some interesting properties, and that's what Haagerup and Musat were exploiting. We realized that unfortunately this A there is no uniqueness. So for a map, this A could be an abelian one, it could be a finite dimensional one, it could be an infinite dimensional one. So there is no uniqueness to this C-star algebra A. Anyhow, if you start with a correlation, doesn't have to be quantum. Any correlation that is maybe local or quantum. If you take the matrix units of Mn as EXA and send it to this element via just sticking this PABXY with the EAB and take the sum over all AB, turns out that there's a linear map, and not only it's a linear map, it's actually more than that. If your correlation is very specific to bisynchronous, then this map is factorizable. And the ancilla or the C-star algebra A could be taken depending on which strategy you have taken. So if suppose you take a QC, then the ancilla could be any C-star algebra with trace, where you have a quantum permutation. If it is Q, then A could be taken to finite dimensional, QA hyperfinite two-one factor, and log could be a million. So it's like, you know, exactly the way you got the representation of OS and plus, you get these maps to factor through those ancilla. And the converse, the some sort of a partial converse is also true. If you map factor through a quantum permutation like this, then the correlation that you get out of this is actually, if you see where the matrix units go, you'll see that those correlations actually satisfy this condition of bisynchronous. So it's like some sort of a partial converse. So that was another aspect of our work, that we could relate these correlations with some completely positive maps, which are quite, it was not, it only made all these nice connections because you had this bisynchronicity, because it gives you a lot of structure to play with. And what I wanted to just mention towards the end is this another concept of these maps is the work with Jeremy Levick. Actually, this should be LR. I don't know why I put LP. So the idea here is you still want to study maps with this property, that factorizing property, but here you don't restrict your map to factorize through a unital. Here you just want a operator in the bipartite system where the operator is basically consists of entry-wise positive semidefinite operator inside that algebra A. So if you remember, your quantum permutation has this property because quantum permutation is constituted of projections. So all projections are positive semidefinite operator. So what if instead of requiring a unitary, if you just allow a bipartite operator, which is entry-wise positive semidefinite, and then let your map factor like this, what can you say? It turns out that even this kind of map have a lot of structure associated with them, comes with some sort of a self-duality of convex sets. And we studied this with Jeremy. Jeremy and I were studying these maps, and there are lots of structure we could find, and this motivated the previous work with one motivated this kind of maps, and we found out some nice properties about these maps. So there are more things I wanted to say, but I mean, I just wanted to stop here with this definition of positively factorizable map. Moving forward with a lot of unknown questions in this work is number one is this Mike Brennan and some collaborators, they proved that anytime you have this star algebra of this graph isomorphism game, you always have a trace. Now it is not clear, and that's what I think that relates to the previous question, that it's whether it's embeddable. It's not even sure that all the bisynchronous game even have a trace. So graph isomorphism game, the star algebra always has a trace, but it is not even clear that every bisynchronous game has a trace even. We can't prove this. For some specific games, yes, we can prove that, like there are results which shows that if you take the algebra, that algebra always has a trace, but in general, we don't have a result. So that's one of the open questions. And the second question, which is still, it's been almost a year, more than a year, we're thinking about it, but we don't know the answer, is this question of almost quantum permutation. So the idea here is to prove this approximate version of which you call this bisynchronous approximation problem. You need to solve a very matrix theory problem, which is here. We are unable to solve this problem. So what the idea here is, you take a matrix, with two norms, and suppose you have a n by n matrix with projections, with the property that it along row and column, it doesn't quite add up to the identity, but it's very close to the identity. So in some norm, let's say 2 norm, it is for given epsilon, you get the sum each row and along each column, the sum up to identity up to epsilon. So it's almost like a quantum permutation, but it's not quite. But if I can prove that there is an actual quantum permutation lying very close to that almost guy, with a delta distance, where this delta does not depend on d, the dimension, then I can solve the approximation problem. But unfortunately, to solve this, I need to solve this problem, and we are still stuck with this problem. We can't find this almost quantum permutation problem, which just says that whether this is stable, the existence of quantum permutation. That means if you're almost very close to being a quantum permutation, is there an actual permutation, quantum permutation that sits very close to that guy, and that closeness has to be independent of the dimension. We still don't have the answer to it, and with these two questions, I think I need to stop. So thanks for listening.
Thank you for a very nice talk. You can also switch on the camera, I think. Maybe. So are there any questions?
Okay, I have a few questions. So what are the examples of this positive factorizable maps?
If you,
I know Sur multipliers coming from self-adjoint matrices, they are, I think, factorizable, right?
Sur multiplier, yeah. So Sur multiplier with your entries of the Sur multiplier coming from a von Neumann algebra as a moment, those are positively factorizable. So suppose your Sur multiplier associated to a correlation matrix, let's say Cij. If you can prescribe a von Neumann algebra with a trace with some positive elements, such that each of these entries Cij can be written as the trace tau of those Vij, those elements in von Neumann algebra. If that is the if and only condition for a Sur multiplier to be a positively factorizable, and based on that, you can produce a lot of examples and non-examples of these maps.
And so this identity tensor tau, I think this is just the conditional expectation, right? With respect to this mn.
Yes.
Is going to this.
Exactly. Yeah. So you're basically taking mn tensor A, and then you're mapping it back to mn, but with this, it's a partial trace. Exactly. It is a conditional expectation.
So one more thing is that suppose you are saying this star algebra associated to this bisynchronous game, you do not know if that is tracial or not, right? All that.
Yes.
So I'm just guessing. So you are saying this, but it looks like you have this synchronous game, then you have more relations, then you get bisynchronous games. So I mean, is it true that this star algebra for bisynchronous games, they are some kind of quotient of star algebras of this synchronous games, or no?
No, we don't know that. It's not quite the quotient, but because you in what happens is in synchronous you have let's say an n by, if you stack up those projections in an n by n matrix with same input and same output, then it has the property that along each row the projections sum up to identity, but you have no control over along the column. So what bisynchronous gives you, it also gives you this freedom that, well, it's not freedom, but it also gives you this condition that they have to not only sum up the identity along row, it also has to have to sum up the identity along column. So that's the basic difference. Whether each bisynchronous is a quotient of a synchronous algebra, I don't think so. I don't know.
I see.
But yeah.
So and did you study this this positive factorizable maps for general fundamental algebra? Because this notion is for general fundamental algebra, right? I mean,
You need to have a trace.
yeah. It's for I mean,
Yes.
that's why I'm saying. So did
Yeah,
you
yeah, yeah.
only for
Yeah,
matrices?
yeah. No. So we studied actually for general polynomial algebra,
Oh, okay.
and there are some results that we have that there are true multipliers that not even finite dimension, you cannot even put it in even infinite dimensional phenomenal algebra. So you cannot have any phenomenal algebra with this kind of property. So yes, when I said in the definition that is a phenomenal algebra, it's any phenomenal algebra. If you see that there are this difference between taking finite dimensional versus infinite dimensional in the work of Haagerup and Musat. So yeah, so it is more general.
Okay, thanks. Thank you.
There is a question in the chat. It's written, any control in ranks of projections or mutual inner products?
In the question of the last question,
Yeah.
No rank criteria. As long as you have a bunch of projections summing up to the close to identity, that's enough. Ranks, at least in this purpose, ranks don't matter. You just need to have those properties. Yeah.
Mm-hmm. Yeah, so I think maybe I have a very simple, I don't know, because I don't work in this area. Maybe Shamo already asked. So do you also have some results in the continuum? Because, here your space is sort of discrete, no? The outputs. So what if...
Oh, yeah. So no, well, not only I mean, this area hasn't evolved so that's why we say it's a finite input-output. No, we actually don't know if you make your input and output to be coming from an infinite set, what happens and how you frame these questions is not really clear. So the continuous version of it, yeah, no, we have no studies on it.
Mm-hmm. Yeah, maybe quantum field theory, they do have something like that, but yeah.
Possibly, but the how you, so yeah, it's yeah, I don't know. Yeah, maybe they usually have the continuum, but in this context, whether
Yeah,
they have it
yeah.
or not,
Yeah,
I'm not sure.
that's not, yes, yeah, sure, yeah. Mm-hmm. Okay, once again, thanks a lot for a really nice talk. And
Thank you for
yeah, hope
inviting.
to see you in future. I don't know when and where, but yeah. Okay, so let's thank the speaker. Let's unmute and clap, or
Thank you.
just give the reaction. So I'll definitely clap.
Thank you.
Yeah. Okay. Yeah, so I'll end. I'm sorry, I'll stop.